And we're back. Welcome back and happy Thursday. Today we will switch gears and look at material for chapter 6 in the book on synchronization. Before we do so, a few administrative bits. The reading, we have added to the reading by the 5th of November 2020. Please make sure you're reading in the text, section 6.1 through 6.8. That's pages 257 through 284. Make sure you're keeping up to the reading with the reading. Again, make sure, please, you are keeping up with the reading. All right, so why don't we begin? Now, synchronization is one of the top issues, practical issues, as it pertains to operating systems. And so the objective of Chapter 6 is to present the concept of synchronization, to introduce the so-called critical section problem, whose solutions to this issue ensures consistency of data shared between two processes. Now, I'm saying processes here, but I mean threads or processes, schedulable entities. It also presents both software and hardware solutions to the critical section or CS problem, and also examines classical process synchronization problems and tools for the solution to those problems. So let's jump right in to the critical section issue to kind of nail home what the point of all this is. And so we have an instruction stream, we have some code, and we have a block of instructions. And this particular block is a function. And we have a bunch of instructions. Here we have k-many instructions. We have the first instruction, second instruction, third instruction, so forth, up to including some k instruction in this block of behavior, this so-called instruction stream. And let's imagine now we had a set of threads. We have n many threads, T1, T2, including up to and including Tn. And these threads are all going to execute some code pertaining to this block, this instruction stream. And within this block, we have a code snippet. And this particular code snippet retrieves a balance based on the name of some accountant associated with a bank, for example. It adds a deposit to this balance, gets a new balance, and then it compounds interest, the balance times 1 point something something, where it's 1 plus the APR. So it compounds the interest and then stores back that balance. So let's take a look at what happens when we have multiple threads executing this instruction stream, and they encounter this particular snippet of code that loads the balance. It performs an operation on that balance, adds a deposit, compounds the interest, another operation, and then stores it back. So let's say thread 1 comes in, and it's executing instruction streams and encounters this particular code snippet within this block. First thing, we have the balance set to 0. And let's say, for the sake of consideration, the APR is 5%. You can't get that with bank accounts these days, but this is just an example. And the deposit is in the amount of $50. So the first thing we do is thread 1 executes the first statement, retrieves the balance, and let's say that balance was $150. And then it adds the deposit. It's now $200. And all of a sudden, we get a context switch. So once that context switch happens, the scheduler selects a new thread to execute, thread 2. And mind you, threads share the same data in the same process. And so thread T2 executes, and it starts executing. First thing it does is retrieves the balance. It retrieves the balance. It's $150. It then goes to add the deposit. And before it can do that, it encounters a context switch. And so the scheduler selects back thread T1 to execute, and the dispatcher does the job of transferring the execution context associated with thread 1 and thread 2 in the right order. And thread 1 is now scheduled on the CPU to execute. So then thread 1 resumes from where it left off, and it compounds the interest given the current balance. It gets $157.50, and then it goes ahead and stores that. Now there's a really big problem here. Thread 1 just lost your balance. It lost your deposit. And this is called a race condition. Both threads are accessing this critical section, this snippet of code that both modify this balance variable. It's being accessed by both threads, T1 and T2, either concurrently, which is in the case of a context switch, or for running these threads on different CPUs in a multi-core, multi-processor system, they're physically executing at the same time. And so this issue where information is lost, it becomes unstable because of two schedulable entities, processes or threads, accessing the same shared variable or critical section. It becomes unstable because they're both accessing and modifying at the same time. That's called a race condition. And so the race condition is the unstableness in this shared variable. The critical section is that snippet of code where this access occurs. All right. And so what we need then is we need a construct, a kind of doorway or barrier. And that this synchronization refers to is mechanisms that implements this type of barrier or special doorway. And this doorway implements this idea of the serialization of the access to the critical section. So what does this serialization mean? It means that only one thread or process at a time can access variables or data structures at a time. So that means only thread 1 can execute in this critical section all of those snippets of code that modify the balance, or thread 2 can execute in this critical section, but not both at the same time. So what does this serialization mean? Well, if we have thread 1 executing, it comes to this barrier, this special construct for synchronization, and it executes this dotted line within the critical section, and then it resumes after the critical section is done. Also, it could mean thread 2, likewise, could be executing in the critical section, and when it does so, thread 1 is not executing in the critical section. It executes all the way through, and then after it's done, it exits the critical section, and it continues or resumes its execution throughout the rest of the instruction stream in the block. And so if we have thread 1 running, we get our balance of 210 after we compound the interest and add the deposit. And then after that, thread 2 goes through and it adds the deposit. So that's 260. Compound the interest makes it 273. And this is the correct status of this particular balance variable in the critical section. And so you could also have thread 1 make its way through and the critical section. And once it's done with the critical section, thread 2 can enter the critical section and start executing. Because thread 1 is now done with the critical section, it's executing after the critical section and is no longer interacting with that shared variable balance. And then once thread 2 is done with the critical section, it resumes its execution just after, in the instruction stream, just after that critical section. And so this is what synchronization is. And it's a top 10 operating systems issue. Really, really important to understand synchronization if you're going to write sophisticated applications, because race conditions can get you in some serious trouble in your programs. All right, and so the synchronization ensures orderly access to the critical section, thus eliminating the race condition, this instability in the shared variable value. Now, of course, if you are implementing a banking server, you want to make sure that deposits don't mysteriously go away. People get very upset about that. All right, so let's go into some background information. Processes can execute concurrently. We know this at this juncture, and they can be interrupted at any time. And when you're interrupted, you only have partially completed execution. And we saw that with that example of this balance being added to with a deposit and interest being compounded. Thread 1 was context switched. It was interrupted through something like round robin scheduling. And then thread 2 was executed. And then thread 2 was interrupted, and then thread 1 resumed. And so this concurrent access or parallel access, I'll add that, to shared data can result in an inconsistent form or value associated with this data, be they variables or data structures. And so part of the goal then is to maintain consistency. And so we need mechanisms in place that will make the execution orderly between two cooperating processes. And that orderly execution can be reflected or depicted as so-called serialized, one at a time, passes through the critical section code. And so to illustrate the problem, in the book, they look at the producer-consumer problem. You have a buffer, and the producer is a process that fills the buffer with data. So we have the producer, and the consumer takes that data out of the shared data structure. In this case, it's a list or queue, and it does something with it. And so we have the consumer-producer problem, and the goal is to fill all of the buffers in this data structure with information. The producer wants to add data, and the consumer wants to remove that data. And so in the producer-consumer treatment in the book, in Chapter 6, we have an integer variable, counter, and this counter is going to keep track of the number of slots in this buffer that are occupied. Initially, the counter is set to 0, and what does that represent? It represents your buffer. Here's my buffer. All the slots are currently empty. And so when the producer produces one, says, okay, well, the counter is going to increment because now you have one of these slots is full. All right, so initially the counter is set to 0. It's incremented by the producer each time it produces a new piece of data put in the buffer. And then likewise, when the consumer removes a piece of data from that buffer, it's going to decrement the counter. And so when you produce, it goes counter plus plus, representing the number of items in the buffer, and consumer executes counter minus minus because it's decreasing the number of data items in that buffer by 1. Okay, so here's some pseudocode that's eerily similar to correct C code. We have a tight while loop, and this is the role assumed, and you can think of this as pseudocode, the role assumed of the producer, or by the producer. And so here we produce an item, and then you go into a tight while loop, and you look to see if the counter is equal to the buffer size. What does that mean? It means the buffer is full. If the buffer is full, we sit in a tight while loop, and here you see it's an empty statement. So the while loop just continues to spin. And so that producer thread, it executes in its instruction stream in this while block, executes the while, and then executes the while again and again and again. Sometimes this is called a spin lock because it doesn't allow the producer to continue its execution beyond this barrier, this point in the instruction stream or barrier. It doesn't allow the execution of the producer to proceed past this point until the counter is not equal to the buffer size. And so the consumer is spinning merrily along. It consumes something. All of a sudden, counter is not equal to the buffer size, meaning the buffer is no longer full. So what does it do? It takes that next produced data item, inserts it into the current position for the buffer, and then it takes this cursor, this position, and it increments it. And so if your buffer starts at 0 and it has a maximum buffer size minus 1, if we're doing zero-space indexing in our list. So it starts out in is here. You store your data item, so there's your data, and then you increment in by 1 modulo buffer size. So in increments, so it goes 0 to 1 to 2 to 3 to 4 to 5, etc. And once in is here, what that modulo does is you increment it, and it ends up going back to 0 again. So it's a ring buffer, if you will. It wraps back around to 0. And so here we have our buffer, and we're doing a ring-based implementation, and the producer is going to insert the data item and then move this index to point to the next item to the right, wrapping around if it goes off the right-hand side of this buffer to the next space, which is going to be in 0, each time incrementing a counter. So once this counter reaches the buffer size, if there's nobody to consume these data items, eventually the counter equals buffer size, and the spin lock prevents the producer from putting in any more data items. So if I have data items everywhere, it goes back to here, it wraps around to the beginning, the count is equal to buffer size, and it will not allow it to insert a new item. Okay, so the consumer then, for the shared data structure, our buffer, well, it makes sure that it can't remove any items if there are no items to be removed. So if the counter is equal to 0, that means that there are no data items in the buffer to be removed, and the spin lock disallows execution of this consumer process to proceed past this empty while. And so the spin lock prevents it from consuming anything else, and then once some item has been placed, the counter is incremented, as we saw before, by the producer, and then this counter then takes the current location where it last should see an output to remove. It indexes that position of the buffer once you have some count or it's non-empty of your buffer, and it consumes it. So after it consumes it, it increments this out pointer. And so we see here this consumer starts taking items from some point called out. It removes the item, and then it increments that index out. And it keeps doing that until out is equal to that last position, buffer size minus 1. It removes that one, and then it increments modulo buffer size, and it now points to that 0th item in the buffer. And so it decrements after removing that item and incrementing the out pointer, the out index, and it decrements by 1. So once it goes to 0, this counter, it is disallowed from removing any more until some producer has come along, placed an item in the buffer, and incremented the counter. And there's the consumer. Now, certainly, the race condition here, if we look at the implementation of producer and consumer, and you can imagine if they were 2 different threads, when you say counter gets counter plus 1, we said before in the CPU, one of the items in the CPU is called the register file. And the register file, we said, are a bunch of registers, a very fast kind of memory, and they store intermediate values. And so underneath the covers, what's happening when you say counter plus plus, you're taking some variable, here's main memory, and there's some position in memory that's accessed by the name counter, and it's loading the value stored at that position in main memory from that address associated with the name counter, loading it into the register file. So here's the initial counter into a register. So then it's the increment operator. So it increments that particular register where the count was stored, and then it assigns the result of that increment back to that location in memory associated with the variable name or symbol called counter. Likewise, when we do the decrement, counter minus minus, well, you take counter from memory stored in a different register, you then decrement that register where it was stored, and then you copy the contents from that register to that location in memory for counter. And so part of the issue that happens with this producer consumer, well, the producer wants to increment the counter in one thread, while at the same time the consumer wants to decrement the counter in another thread. So what if you had the execution interleaved between the first thread for the producer and the second thread for the consumer? So let's say you're doing the count for the producer, counter plus plus. You take counter, put its value into register 1, and then you increment register 1. And so now register 1, let's say the count was initially 5, you increment it. Register 1 has the value 6 now, because 5 plus 1 is 6. Now before the contents of register 1 can be put back into counter in memory, the second thread, the consumer, runs. It loads the contents of counter into register 2. Well, counter is 5. Now register 2 is then decremented. 5 minus 1 is 4. And then at that point, context switch happens. Now we're back to thread 1 for the producer. It says, okay, well, now let me take the contents of register 1 and put it into memory at the location called counter. So then all of a sudden, another context switch happens again. The consumer finishes its execution, and it completes by storing the contents of register 2 from the register file into the variable counter in memory. So now all of a sudden, counter has a value of 4. Okay, and so this idea of a race condition can occur because of the interleaving of two threads. When you context switch one and context switch in another, what happens, as we said before, some of the execution context for a thread, it includes your register file, it includes your stack pointer, and it also includes your program counter. And so when you context switch from one thread to the next, well, the register file information is unloaded and then rewritten, loaded from the other thread execution context. Okay, and so this instability will lead to different values of counter in memory based on the context switching and which one executed first, or which one preempted the other, or when they were swapped in and swapped out, when they were context switched by the short-term scheduler. Okay, so let's look at the critical section problem. Now, the critical section problem says to consider n many processes, P0 through Pn minus 1, and each one has a critical section segment in its code. Now, a process could be doing a bunch of things in its critical section. It could be changing variables, it could be updating a table, writing a file, all sorts of stuff. When one process is in its critical section, no other process may be in its critical section. You want to make sure we have this serialized execution in the critical section between all of these n many processes. And so the critical section problem is then to design some solution or protocol to follow that will solve this issue, how to serialize access among all the processes to their critical section. And so each process in this solution must explicitly ask permission to enter the critical section. This is the barrier that I alluded to before. And now this entry section is where it does that ask. And now you also have the critical section following this entry point, this entry section. And then after the critical section, you have the exit section, which is where the release of this access occurs. And then you have the remainder of your instruction stream. So you have the critical section, you have the entry section before it, where access is granted or denied. And you have the exit section where access is released, and then you have the remainder section. And so the general structure for a process, you have a tight loop, and it could also be a thread. You have the entry barrier, you have the exit section, and then you have the critical section in between. And so it's in this critical section that I alluded to at the beginning of the slide deck. That's where the modification of those shared files, variables, data structures, etc. occurs. And so the orderly execution of threads or processes in this critical section means serialized, only one at a time can be executing in this critical section. That's how you guarantee the stability of those data structures within the critical section. Okay, so let's take a look at an algorithm, and this is kind of pseudocode-ish for the ICE process. Now, it doesn't matter what I is. If you have the ICE process, every process that's not the ICE process is the JAIF process. And so here we have our loop. We have the entry section, and we have just a while loop. And this variable turn is used to determine which process is going to have the ability to execute in the critical section. And so this quote-unquote spin lock, it's a barrier, and you request access by making sure this turn variable is equal to your particular process number. And so if your turn for process I is equal to J, your execution stays in this while loop and it can't go further. So it's effectively locked out of entering the critical section. So once the jth process somewhere is done with its turn, this turn variable is set to some other number aside from the j. And one of them is going to set it to the ith. So then once it's set to the ith, this turn variable, this while condition is false, and it comes down execution for this ith process, which was stuck here in this entry section. This barrier or spin lock, as it's called, it's now executing in its critical section. And so then after the process I is done with execution of its critical section, it has the exit section here. And what it does on the way out after the critical section, it sets the turn to some other process number. So some other process can become unstuck and execute in the critical section, therefore modifying the shared variables. Okay, and so the solution to the critical section has to have three main features to it. One of them is called mutual exclusion. What this means is that if a certain process, the ith process, is executing in its critical section, then no other process can do that. And in the case of this example before, once if the ith process can't get past this barrier until turn is equal to I. And when turn is equal to I, the ith process executes in this critical section, but all the other processes, process j, for all values of j not equal to I, they cannot enter the critical section. That's what mutual exclusion means, this serialized access to the critical section. Then the second feature is this idea of progress. And so no process, if no process is in the critical section and there's some process that's trying to get into it, then the process that will enter the critical section next can't be delayed indefinitely. So if you want access and no one else is in the critical section, you're going to get access in a reasonable amount of time sometime soon. You can't be forced indefinitely to wait for access, to wait in the entry section for access to the critical section. And so when you have that request has to be satisfied if no one else is executing. And then this last part is important. It's called bounded wait. A bound, meaning an upper value, must exist on the number of times that other processes can be in the critical section after one process has made a request. So that means a kind of fairness. If you have n processes and one of them requests access, the other n minus one might be going to the critical section before that process that's requesting, but at some point eventually it's going to get its turn to enter. And so you can assume that each process executes at some non-zero speed, takes some time. And so all the other n minus one processes, in the least, the time they take to execute instructions in the critical section, after that amount of time, that one process that's waiting should be given access. And so this bounded wait means that you don't wait forever to gain entry to the critical section. There's an upper limit on how long you wait. Okay. And so in handling the critical section in the operating system, remember that when a system call is executed, a trap occurs. It's a software interrupt, and that transfers control to the OS kernel that performs the details of the system call on behalf of that program. So in essence, that program is almost like it's executing in kernel mode, whereas really just the kernel is performing some function on its behalf. And so when you're handling critical sections in an operating system, there are two different choices that you have to think about. One is preemptive, and preemption means that you can allow a process to be preempted even when it's running in kernel mode, or even when the kernel is handling a trap on behalf of that process. Non-preemptive critical section handling in the OS means that it waits until the kernel exits, right? Or some natural blocking call, like waiting for I/O, occurs, and it voluntarily yields the CPU. So non-preemptive means that the kernel is allowed to get to a natural pause point before the particular process can be taken off the CPU and put back on the ready queue or some wait queue. All right. And so essentially what the non-preemptive case means is that you're free of race conditions in kernel mode because it's allowed to finish what it's doing if it's in kernel mode. All right, so let's take a look at one of the solutions. One of them is called Peterson's solutions, and this is a very famous one. And so Peterson's solution gives a good algorithmic description. Now, this is just an algorithm. Some of the pseudocode looks like C, but it is an algorithm. It gives an algorithmic description of how you solve this producer-consumer problem. And it's a two-process solution. And so it's from the perspective of two different processes that want to access the critical section. And so one of the assumptions is that when you load a value from some variable, or you store a value to some variable, that these instructions for doing so, copying to the register, copying to memory, so forth, they're so-called atomic, meaning that they can't be interrupted. And every chipset, its assembly, has a so-called set of atomic instructions that are allowed to complete their execution before preemption occurs. And so if your quantum of time and round-robin scheduling has been exhausted and you're in the middle of an atomic instruction, that instruction will complete before the preemption occurs. And so the two processes in Peterson's solution share variables. One is called the turn variable, and it'll store an integer describing which particular process is the one that should be given the chance to access the critical section. And then a flag is a 2-byte or 2-Boolean array, an array of 2 Booleans, flag array. And this turn indicates whose turn it is to enter, but the flag array is used to indicate if a particular process is ready to enter the critical section. So for process I, if flag, the ith position, is equal to true, it means that PI is ready to enter the critical section to perform the actions associated with modifying data structures in that snippet of code for the critical section. And so this is the algorithm for the ith process. Again, we have our entry barrier, and we have our exit barrier. So entry, we request access to the critical section. Exit, we release that access. And so we start out, and you set your flag to true, meaning that you intend to access, you're ready to access the critical section. And now turn, well, turn is set to J, meaning that the turn is given to another process. Now the next thing that happens, you sit in a tight while loop, and this is the barrier part. It has a spin lock. Two conditions have to be the case. That it has to be both the turn of process I in order for it to enter, and it also has to be ready to enter. So here, as long as some other process that's not the ith process is ready to access the critical section, and at the same time it's that process's turn, well, process PI is just going to sit and spin in that empty while loop. And so it is not permitted, process PI is not permitted to leave that entry section in its execution of instructions in the instruction stream. It won't leave and it won't access the critical section. Now, all of a sudden, some J's process is finished and it is no longer ready because it's done with the critical section. And then at some point, the turn is going to be set to process PI. Okay, so once that's the case, if either process PI is ready and process PI, it's also its turn, then process PI can get back past this particular entry barrier and enters the critical section. So now once it's done with the critical section, it sets its flag to false. And it says, okay, I'm no longer ready to execute the critical section because I've already finished doing that, and it executes now the remainder section. And so at the same time, we have process PJ doing the same thing. It can say, okay, well, next it's going to be process PI's turn, and when I, process PJ, am done, I'm going to set my flag of J's position to equal false. And so once I do that, this condition for PI is no longer true. It unblocks or gets past this entry barrier, and its request is satisfied to enter the critical section, and process PI does so. All right. And so with Peterson's solution, it satisfies all the things that a requirement requires for critical sections. Mutual exclusion is preserved. Yes, the ith process only enters the critical section if either the J's process is not ready, flag J's position is false, or it's the turn for process I. The progress requirement is satisfied because if there's nobody who's ready except for process I, it's going to enter the critical section, and the bounded wait is met because after the execution of each one of these J processes, each one is going to have a statement in the exit section that looks like flag of J is equal to false. So if all of the J processes execute that, well, the only thing that's left to be true is flag I. And so you have n minus 1 processes that will be false, and the 1 process for process I is going to be set to true. And so eventually in its execution, process PI is going to enter. And so progress is maintained, and this bounded wait means you're going to wait no longer for n processes. You're going to wait n minus 1 times the amount of time for each process to execute in the critical section. And so it's bounded. It's going to be less than or equal to that amount. Okay. So with that, that's Peterson's solution. We will end there, and we'll pick back up on Tuesday. Until then, as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.